So, you lucky people, last time I was speaking in front of you, I introduced a trilogy in 4 parts, as Terry Pratchett once famously said. This is even better. It's a trilogy in 5 parts this time, and we will be dealing with open loop ground source systems. This session is to kick everything off and to set the scene, set the context for the rest of the discussions. I'll be coming back on the 5th session to wrap everything up and then to talk about what happens above the ground when we're talking about open loop ground source heat pump systems. In the middle, we've got some genuine world-class experts to talk about what's happening in the ground with these systems. It's a very different kettle of fish from closed loop, and I'll talk about the differences between the 2 technologies in just a few minutes. So without further ado, what I'm going to talk about today is, as I say, I'm going to discuss the differences between open loop and closed loop and the interesting points and important points that you need to be aware of if you're getting involved in these systems. The second thing I'm going to talk about is system geometry. I'll be talking about how the systems are typically put together, and I'll be elaborating a lot more on what happens outside the ground in the final session of the series, so please just be aware of that. Next thing I'll talk about is how much water do we need? How much water do we need to feed one of these systems? And how much water is available, and how we do a very early first tier assessment of that. We'll then talk about the space and separation requirements for water wells, and before finally summarising the next steps and then handing over to the following speakers for the next few sessions. Just to note that I'll be focusing on boreholes today, so water wells as a source for ground source heat pumps. But most of what I'm going to talk about today does apply to other forms of open loop systems, so using surface water, maybe canals, rivers, lakes, the sea, and so on. The other thing I'd like to point out is that whilst most of this series will talk about systems at the larger scale, at the commercial scale, particularly what I'm talking about today and some very specific points I'm going to talk about on licensing are equally applicable to the very smallest of open loop systems. Okay, so that being said, and without further ado, let's get into a discussion about what the differences are between open loop and closed loop. So first of all, on the downside with open loop, there's nothing you can do about it. There are inherent risks in going open loop. And what I'm talking about there is it's perfectly possible to drill a very well constructed water well and get no water or get less water than you need to for your scheme. So it's very important to realize that there are inherent risks with open loop that just don't exist or don't exist to the same extent for closed loop. Now, I'm definitely not saying that open loop's a bad technology. What I'm saying here is you need to be aware of those risks, and you really need professional help, particularly at the commercial scale, to understand what those risks actually are. So closed loop, as I say, is a lower risk solution. Why is that? Well, because we are putting pipe in the ground to a specification, and we can measure everything about those installed boreholes. And so we know and can de-risk the solution right from the design phases. The second downside to open loop is we do have licensing requirements. Now, there are differences here between small schemes and large schemes. In England and Wales, there is a threshold of 20 metres cubed a day, below which you do not need Environment Agency licensing. Above 20 metres cubed a day, you absolutely do need Environment Agency licensing. It seems that some people have been saying that if you put the water back into the ground, i.e. you're not consuming or taking out of the ground and leaving it out of the ground more than 20 metres cubed a day, you also don't need licensing. That is absolutely and categorically incorrect. If you are taking more than 20 metres cubed a day from the ground, regardless of what happens to that water afterwards, whether it goes back in or not, you absolutely do legally require a license from the Environment Agency. Now, the licensing requirements are complex. They do take a long time, and I'll talk about that in a little bit of detail later, and that will be gone into in very great detail later on in the series. So we do need licensing there are licensing requirements. Just to complicate matters, in the part of the world where I come from, things are different. In Scotland, GSHPA is the licensing authority, not the Environment Agency, and they do have different requirements. So in some instances, GSHPA will accept a non-consumptive scheme of whatever size, i.e. you're taking all the water back into the ground that you've taken out of the ground. They will allow that to go through without a license, but that is not an excuse not to involve them. You absolutely must involve GSHPA in any water well based systems in Scotland. On the upside, from a closed loop point of view, there are no licensing requirements. However, there are best practices and standards that we need to work to. The best standards that are applicable to the systems are maintained by the Ground Source Heat Pump Association, particularly the vertical borehole standards and the environmental standards, which were written originally by the Environment Agency, but are now maintained by the Ground Source Heat Pump Association. So we're dealing with a lesser level of regulation for closed loop than we are with open loop. Because of the licensing requirements, it generally takes longer to get to site for open loop. So the pre-application process for a license can take about 6 weeks, which limits the fact you will not be able to drill until you've got that in place for anything above 20 meters cubed a day. And we can start on site immediately with closed loop. We can turn around a design very quickly and we can be drilling the next day. There are slightly higher ongoing maintenance requirements for open loop. So we are dealing with water that is not treated in an open loop system. And anytime you change the temperature of water that's not treated, anytime you violently move water around that's not treated, the chances are you're going to get some minerals depositing out of solution. So those minerals will generally end up in your heat exchangers for your system, and that maintenance requirement needs to be considered, as well as pumps down wells, for example. So there are higher maintenance requirements. And conversely, with closed loop, where we've got a treated loop of fluid in the ground, then we have lower maintenance requirements. On the upside for open loop, the design is simpler. Now, the next session is going to be about the high end of open loop modeling. Now that is incredibly intensive, but isn't required on most systems. So it does have at the core level a simpler set of designs, and I'm actually going to talk about the design process in just a couple of minutes. Now, if you compare that with closed loop, to do closed loop design at any size properly, you really need to be using bespoke software, and know what you're doing with that software is very important as well. So there are slight differences there. In most cases, open loop will be a simpler design process than closed loop. Open loop requires less space. I'm going to come back to this in a moment. And what I mean by that is each borehole in open loop gives you, or can give you, an awful lot more thermal output than each borehole in a closed loop system. So a single open loop borehole pair, one taking water from the ground, putting back into the ground, each being just a manhole, when it's completed, could give you a megawatt of output quite easily. Whereas a closed loop borehole, you're talking about somewhere between 5 and maybe 20, 25 kilowatts at absolute best. So it is a more space hungry solution. Generally also, open loop is a lower installed cost. When you do the sums, when you look at feasibility studies, as I do every day on these systems, it generally comes out that open loop is a cheaper solution. The quantum of that can vary, could be 10%, could be 20%. Those are the kind of values that you would see in terms of savings of open loop systems over closed loop systems. So closed loop systems are generally slightly more expensive. And then finally, there is a point I'm going to make on both sides. Both can be more efficient. There are differences in how they operate. The physics of the two are quite different in some ways. And that can mean that an open loop can be more efficient in some instances, and a closed loop can be more efficient in others. So let me give you an example to illustrate that. If you are looking at a heating only system, it is very likely that open loop will result in a more efficient solution than closed loop. And the reason for that is that the water will be coming from the ground at a constant temperature, which will be probably well above zero. In fact, it needs to be well above zero. It'll be somewhere between the 10 to 12 degrees C mark. So you've got quite a warm source there. In order to keep the size of a closed loop sensible, we can often be driving the loop temperatures down to around the zero mark. So we've got a colder source and therefore a slightly less efficient solution. However, if you've got a nicely balanced heating and cooling solution, where you've got heating and cooling loads going on either simultaneously or interseasonally, then you can actually manage a loop temperature to optimize efficiency, a closed loop temperature to optimize efficiency in the way that you just simply cannot do with open loop, particularly if you've got any groundwater movement going on there. So any heat you're storing in the ground could get washed away. So there are differences. It's complicated, and so in order to model those, it's very important that you really seek expert advice if you're getting involved in these systems. Okay. I'd normally at this point look at my audience and establish eye contact and try and get some feedback, but I'm just going to have to soldier on in the world we live in today. By the way, I forgot to welcome you to the first full day of Heat Pump UK after the announcements from the government yesterday. So I think we can all pat ourselves in the back. There's a lot of heat pump specialists around the table. It's great to see the industry getting a shot in the arm like we got yesterday. So to talk about what a typical system looks like, and this is an absolutely typical open loop ground source system. This one happens to have boreholes under the basement of the building, so probably installed during the build of a city centre building where we've got no space outside, and that's perfectly doable, done it many times myself. What we have here is an abstraction well, this one here, that's taking water from the ground, and we've got a recharge well here, which is putting water back into the ground. There's a pump here down the bottom of the well, which is pumping up the cable or pipe on which it's supported. It then pumps through a heat exchanger, which keeps that untreated water away from the heat pumps and then back into the ground. Then you've got a closed loop inside the building, which can act to recover heat between simultaneous heating and cooling loads. And more importantly, it keeps that untreated water away from the heat pumps. Now, it is absolutely possible to take that groundwater and put it directly through the heat pumps if the heat pump is designed to take groundwater, and there are special heat exchanger designs to allow that. However, certainly in larger systems, it is almost always the case where you break the two circuits, keep them apart, so as to protect the heat exchangers inside your heat pumps, which are much more difficult to replace or repair than these external plate frame heat exchangers, which could go in duty standby pair, so you don't even have to take the system offline to do some maintenance on those heat exchangers. What I will do is later on in the series, as I mentioned earlier on, I will talk about the architectures of heat pumps inside the building here. I've just shown it very simplistically in this schematic just for ease. Just to go into a little bit of detail on how these wells function, and this is really just lining things up for much more detail later on in the series, but you'll see that the water level here in the abstraction well is lower than the water level here in the recharge well. That's because this pump is drawing that water level down. It's called drawdown, and it's down from the standing water level in the ground. That pressure effectively drives water into the well. Water then falls in from the surrounding ground into the well. The opposite happens in the recharge well. So we're actually using the weight of the water to push that water back into the ground. And you don't have to be an expert in hydraulics to recognize that if you've got water being pushed into the ground here and drawn out of the ground here, it's very likely that that water is going to migrate between these two wells. And I'll touch on that because it's a very important concept in working out how far apart these water wells need to be. Again, I'd love to ask for questions, but please do put them in the chat. So, first question, when we are assessing, is an open loop going to be viable for us at a given location? First thing we need to work out is how much water do we need? Well, it depends on what peak loads, heating and cooling loads, you're looking for, how efficient your heat pumps are, and what the groundwater temperature is and how much we can change it by. And always, 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 we've got to consider the natural properties of water and the laws of physics. Please do not, in any ground source systems or any engineering, try and overcome the laws of physics. You will lose. And the natural properties of water are very, very important in these systems. So the specific heat capacity of the water, the freezing point of water is a limiting factor on the design. So that depends on how much water we need. So to a first approximation, that's the sums. You take your peak load, you multiply it by the efficiency, the COP of your heat pump at the design condition. You take one away from it, you divide that by the COP again, and then you divide that whole lot by 4.2 times delta T. So let me just tell you what everything is here. So the COP of the system is how efficient is the heat pump, so how much electrical energy is consumed for a unit of heat that's delivered, or more accurately, how many units of heat that's delivered for every kilowatt hour of electricity bought. And that means that in a heating system, your electrical energy is actually supplementing the heating going into the building, and it actually reduces the flow required because some of that energy is now not coming from the ground, but is coming from the electrical supply. Conversely, on cooling, you can see that this COP correction term here is upside down. And what that means for the non-mathematically minded is that the electrical energy that your heat pump is now consuming increases your flow rate because you have got to put that into the ground. It's not used to you in the building. This 4.2 is just simply a way of dealing with the specific heat capacity of the water. And then the delta T here is the temperature difference you're applying to that open loop circuit. So what's the delta T you're putting on it? Water might be coming from the ground at 8 degrees up in Scotland. It might be coming from the ground at 14 or 15, even 16 degrees in London. And so you've got a different set of design criteria. If it's coming out of the ground at 8 degrees, you definitely don't want to be putting more than a 6-degree delta T on it, temperature difference on it, or else you're getting uncomfortably close to that interesting point around 0, where the water's going to freeze and it's going to wreck your heat exchangers. Whereas in London, you might get away with more, but you've got to consider the fact that the Environment Agency and GSHPA consider heat to be a pollutant, and so they will have a view on what delta Ts you can use on any given system in both heating and cooling. Typically 10-degree delta Ts are accepted, but it is part of the process with the Environment Agency. So there is a 2-3 minute crash course in open loop design. Big disclaimer, just look after your PI and get a specialist involved with this type of work. So we know how much water we want, or would like to get, and we now need to work out how much water is available. This is an example of the online data you can get with data of all the water wells. This is central London. There's Westminster here. And each of these triangles is a water well, a licensed water well within London. So online information is available and it is very extensive. But you really want to limit the use of this online information to early days feasibility, and you certainly want to get an expert involved very early who will not only be able to access this data, but will be able to interpret it from years of experience. It's very important to understand that in the UK there are a large number of different types of aquifer, and they have different properties, and it takes a bit of experience to understand how they're going to behave. Hydrogeology is a science. So as I say, it takes years at university. A good friend of mine, John Finlay, in the industry, often relates the example that when a customer quibbles about a bill for hydrogeological services, he often says, well, he or she wouldn't quibble like that if it was a lawyer putting a bill in. You might not like it, but you're paying for years of training and experience. And it's exactly the same as in that from a hydrogeology point of view. And by the way, I'm not saying that hydrogeologists charge as much as lawyers. That's not what I'm saying in any way, shape or form, but it is a skill. It takes years of experience and training to be a hydrogeologist. So as I mentioned earlier, there are many, many major aquifers in the UK. Classic examples are the chalk in London, chalk which sits underneath a layer of clay in London. It's what's called a fissure flow aquifer. So the water lives in cracks and fissures in the chalk. And that's an example of one of the risks with an open loop project is if you don't hit those cracks in the chalk, you're not going to get the water out of the chalk. So it's very important to get involved. You can see here there's a cluster of lots of wells over here in East London. That could be because there's readily available water there, That could also be because there was industry there in the past to use the water. So there can be varying different reasons. And again, it takes experience. The other thing I would point out is that you may see well records online with a yield of, say, 10 litres a second. That doesn't mean to say that you can't get 50 litres a second out of that aquifer. It's just that the people who were drilling that well only were looking for 10 litres a second. So again, you've got to taper this with a bit of experience. There are many more smaller aquifers in the UK as well. There's a brilliant wealth of knowledge of specialists who deal with a lot of these smaller aquifers. A great example is I was once giving a budget price for an open loop system to a client in the southeast of the country. I was budgeting 60,000, 80,000, that kind of level of cost for a pair of water wells. A local driller came along and said, "I'll do it for 15,000 for you." And that's local experience. They know what they're doing. So it's very useful to gain that local knowledge as well. So once you've had a look at things, I would really strongly recommend that you get a water well prognosis report. The British Geological Survey provide these. They're at a very reasonable cost, and they are excellent reports. There are other companies around the country, so commercial organisations, who will deliver the water well prognosis reports. There's companies like myself, Carbon Zero Consulting, a lot of the other member BA Hydro Solutions, other consultant member companies of the Ground Source Heat Pump Association, who will give you not just a bespoke report for that location for water yields, but also what the implications of that are specifically for ground source, which can add a lot of value to projects. So, as I say, specialist advice is absolutely essential to start developing these designs. And what I would say is it's easier and probably an awful lot cheaper than you think to get that specialist help in early in your project. And we're seeing a lot of demand for that service as an industry. So please, please, please don't DIY one of these projects. It can be a recipe for disaster. So final couple of bits, space and separation requirements. The space required between boreholes is one of the most difficult subjects to deal with. And the next presentation in the series will be all about how we model that in a lot of detail. The rule of thumb is 100 metres is adequate separation between wells that take water from the ground and wells that put water back into the ground. I can tell you I've got successful projects with spacings as low as 35 metres between those obstruction and recharge wells. So whilst a rule of thumb is helpful to get things in your mind, it is absolutely not a definitive statement of the space requirements. I did mention earlier on that open loop requires less space. What I mean by that is the finished well is very small. This is a manhole here you can hopefully just about see in the background with a wellhead in it. An open loop system in its simplistic form would require two of these 100 metres apart, and you've got a functioning system. On the other side, I mentioned systems with 35 metre spacing. I've seen a system fairly recently with 65 metre spacing, and it's in terrible trouble because it's getting a short circuit between those two wells. So it does require, again, expert help. So finally, we've decided an open loop is viable for us. So what's next? What's the next steps? So, as I mentioned, engage a specialist. Second thing you must absolutely do is engage a specialist. And of course, the third thing you must do is get specialist help, get somebody involved with you. Beyond that, it's into looking at the borehole design, the system design, and more detailed viability for the project. The desktop assessment that's required for open loop is a higher bar than is generally required for a closed loop system. You then start to talk to the Environment Agency about the process, or in Scotland, GSHPA. The Environment Agency have what they call a pre-application process, which is incredibly helpful because it allows you at low cost to assess whether the Environment Agency are likely to have a problem with a water well system at that site. So it's a very low cost way of assessing the viability of a system. That process is about 6 weeks and can run in parallel, with the detailed design. And then you're into employing contractors and getting drilling. It really is that straightforward a process, but it is a bit more time consuming. Just bear in mind that when drilling is complete, and again, this will be gone into in a lot more detail by the other speakers in the series, test pumping is required, and then there's a statutory licensing process that the EA then determine what that license is going to look like after that test pumping is complete. The whole process can take a year or more to establish the wells and get them into use. And then remember, as I say, post drilling, the EA process can take 5 months before you're at drilling. And of course, did I say engage a specialist? I think it's very important. Maybe you've got that message for today. So hopefully Laura's joined us and we can start to take some questions. Charlotte?
Okay, Chris, we haven't got Laura.
Okay. Well, shall I try and deal with the question?
There is one question in the chat. Yeah, there's just one in the chat there now, right at the bottom that you can see.
Okay, so from Becky Taylor, thank you very much, Becky. If heat is a pollutant, is there anything regulating the use of loop pipe in closed loop boreholes that enter the water table and would effectively be removing temperature from the water constantly, therefore cooling the water? Okay, so does the same requirements of heat as a pollutant require get involved in closed loop? Is a summary of that. That is covered in the Environment Agency standards on ground source systems. They require the system to be sustainable. Now, they do not define in detail what sustainability is, but what the industry interprets that is that it reaches an equilibrium. So that heat exchanger in the ground in time reaches equilibrium within a sensible set of temperature parameters. And the temperature parameters at the moment, the bottom end of it is 0 degrees C, returning to the heat pump under the MCS regulations. The higher end is less well defined, but it's probably likely to be defined by the performance of your heat pump. So slightly, not a straight answer there, it isn't as clear. Joseph Ireland, question from you. Have you been involved in any open loop aquifer thermal energy storage projects? Yes, I have. I'm researching this technology at Queen's and Belfast. Good luck with your studies. And you're working in the Sherwood Sandstone aquifer. Super. Sherwood Sandstone, just be a little bit careful as you move further north with water quality in that aquifer. It can be a slight challenge for you. And again, later in the series, water quality will be dealt with in a bit of detail. Yes, I've done aquifer thermal storage systems. It requires a level of modelling and a level of understanding of the aquifer which is substantial. You need to make sure you really understand what groundwater movement looks like in that aquifer. I would say that the best person to go into a little bit of detail, Joseph, with is Hugh, who will be handling or looking after the next in the webinar series. But in the meantime, if you've got any questions, please do feel free to contact us and we'll do our best to address them. I can either do it myself or pass on to other colleagues who may be able to help you. Is there anything anybody else would like to ask?
I think there's a question
Dave.
there just above. Yeah.
Okay. Dave Banks has come in with a nice question for us. Charlotte, sorry, you're breaking up a little bit. Maybe it's just me. Dave's come in with a nice question. Thanks for the summary. Happy to help. In order to maximise groundwater delta T, I guess we are talking about manipulating flow rates and temperatures either side of the heat exchanger. Exactly. That is exactly the design process we go through. Are you aware of heat exchanger suppliers who are really up to speed on understanding ground source heat pump industry needs? What I would say on the positive side, the likes of Grumpus pump manufacturers really have put a lot of time and effort into understanding the needs of both open and closed loop ground source systems. From my own experience, and I'm only speaking from my own experience, I haven't seen that level of commitment from the heat exchanger manufacturers. I do fairly frequently have fairly difficult's the wrong word, but fairly lack of understanding type questions coming back from heat exchanger manufacturers. So they don't, I think, understand the variabilities we've got in the design and the things we need to absolutely achieve, whereas they're perhaps used to different things when you're talking about heat exchangers inside buildings. But there are heat exchanger manufacturers who build heat exchangers that are absolutely more than capable of dealing with groundwater in the long term. But yeah, maybe some education would help. Maybe, Charlotte, in a future session, we could perhaps talk about heat exchanger specification and maybe get somebody from heat exchanger manufacturers involved in that. Would be a good one. Thanks, Dave. Yeah, you're struggling as well. They're saying there's a question above the one from Peter. Okay, Peter, missed that one. No, I think I've covered it, have I? Ah, here we go. From Peter McAvoy. Hi, Chris. Ever come across any problems with reduced... I got it, Charlotte, sorry. Any problems with reduced quality water, i.e. high nitrate or local contamination, in terms of being allowed to return to the same aquifer? Okay, I've not had myself any problems returning to the same aquifer. There are often concerns, the second part of your question there, Peter, about saline intrusion. It's very likely that as part of the pre-application process with the Environment Agency that they would flag that there would be concerns about pollution in aquifer and mobilising those pollutants around. So they would probably pick that up very early days in the project. Water quality will be a subject that we're coming back to later on in this series. So Peter, please join again for some of the later sessions. But yeah, there are specific aquifers that it's unlikely you would get a license for, even a non-consumptive scheme, because of pollution and so on. Less likely in deeper aquifers, as to be said. Have I covered everything, Charlotte? Think so.
Yes.
Okay, super. All right. What's the time? How are we doing? More than happy to take more questions if anybody else has them. But if that's enough for today, let's wrap up. And please encourage you to attend the rest of the 4 sessions, which will be in a lot more detail than today, which was really, as I say, just setting the scene. So thank you very much indeed, everybody, for attending. And thank you to those who will no doubt look at this online. And we hope to see you again next week.